Sarap! Kain na kayo! Kain na kayo!
Yes! It's too hot!
Chill, bro. Don't you know it's hot?
Can you eat while it's still hot?
So what? Cold soup still works.
It's getting cold.
Wait, did you say it's getting colder?
Yeah.
It reminds me of Newton's law of cooling that we discussed in class.
Are you really bringing science into breakfast?
You know what? Let's just watch TV.
Alright, hello there to everybody. So for today, we are back here in the virtual explanations, right, where we had a skit on our family where the assumption of a burning noodle and how it cools down. Now, these children already explained how Newton's law of cooling works, and let's just go on straight with the calculations. Here we have a differential equation from Newton's law of cooling, which is, by the way, a decay as it decreases over time. So we have this equation included and the general equation for the solution. Here we have the known values for the time, where the initial, and the ambience, where the initial and the ambience would have that certain difference. Plugging those into our equation, we have where 40 degrees after 5 minutes, and we have the ambient temperature of 20 degrees. We also had a 50 degree, where the initial temperature of that soup or the noodle, and we can easily substitute that to the equation where we could have 40 equals to 20 plus 50 minus 20, then e raised to negative k times 5, where we have 5 as our 5-minute time. And here in this equation, we would be explaining and simplifying how we get our k function, or the k constant, or the rate of cooling. Simplifying these, we will eventually get 20 over 30, or basically 2/3, and equal to the cancellation of that constant factor of c e raised to negative k times 5. And transforming those, we can basically have the ln of both sides, which is the ln of 2/3 equal to the ln of e raised to negative 5k. And in order to reduce that further, we would have ln then e would be canceling out, which would result in just a negative 5k. And we need the k, so we would definitely divide both sides by negative 5 in order for the k to be alone. So that would result in an ln of 2/3 divided by negative 5, which would get us to 0.08. And basically after that, we could just plug it back into the values and we can eventually get our own time. And after plugging these values, we will get 5 minutes. And that is how fast the soup from 60 degrees, from 50 to 40 within 5 minutes.
So if I wait longer, my soup will cool down faster at first?
Yeah, exactly. At first, the soup is hotter than the room, so it cools down. Then it cools, the temperature difference gets smaller, and the cooling slows down. That's what the equation shows.
Newton's law of cooling says the rate of cooling depends on how much hotter the soup is compared to surroundings. The bigger the gap, the faster the lid closes. Okay, so the science actually makes sense now.
I told you so.
Hoy, ano ba? Ipin mo yung channel! Nanonood ako ng balita eh!